All right. Hello, everybody. My name is Ethan Kenny. I'm the project manager for the University at Buffalo Lunabotics team. Um, this is our preliminary design review. I'm glad everybody was able to join us this evening. And for this review, we will be going briefly over last year's design and things that we want to improve for this year. We'll go into the overall plan for this year, what we've done so far towards the competition, what we plan to do from now moving forwards. If you have any questions, please feel free to interrupt. We're going to go over a lot of stuff in a short amount of time, and we'd rather you ask the questions before you're able to forget it. We're also recording this meeting and planning on posting it online. So if you would like your name or your voice to be removed from the recording, if you ask a question, please let me know.
All right. Well, my name is Dylan. I'm one of the lead systems engineering, and I'll just be going over some quick introduction about what the project is, um, what happened last year, and just some logistics. Just go through a little bit quickly. So we compete in the NASA Lunabotics competition, which is a collegiate competition where teams design lunar rovers to autonomously dig soil and then dump them into berms. Pretty much, we build robots that dig soil on their own and then they dump them in a separate area. And you are rewarded based on different factors. So, first off is how much you dig compared to how much you weigh. So, there's some trade-off between heavier rovers digging more and lighter rovers digging less. But you also get points based on how autonomous you are, how dust-proof you are, and some other just like how realistic can it kind of be. And for this competition, we have multiple deliverables throughout the year, but then in May, we fly out to Orlando to compete in UCF. And then the top 10 placing teams in UCF then go to KSC for like a separate competition. So it's kind of two competitions in one. So just for a quick recap of last year. So last year was our first year competing, and we were able to take home the best first year presentation award. In terms of our rover, we were pretty middling in terms of points. Um, our entire rover was pretty much designed in about 3 months by four people. So it was designed very fast and budget friendly. It was our first year, so we had a lot of questions and didn't know a whole lot about the competition going into it. But this year we know a lot more. Um, just some takeaways from last year is that we overall liked the overall design, but the poor implementation of it really held us back. So just for last year's design, I'll do a quick recap. It was a rotating drum that rotates clockwise to dig and then counterclockwise to dump it all out. So it's just one motion for digging and dumping. We had two linear actuators on each side that raised and lowered the drum, and then we had a motor attached to a pulley with a like, elastic belt that would spin the drum. Um, Overall, for this year, we want to optimize what we had. We want a smaller chassis with a simpler cross section to reduce some wasted space and minimize some of the more empty space. We want to redesign the entire drum excavation system. So that's from the drum design, its geometry, and how it's fabricated, how we raise and lower it, and then how we spin it. And then we also want to redesign the wheels using certain test apparatus that we'll get into a little bit later. So for just a quick glance of where we are, this is a preliminary design review, so we're still very early into our design phases. We're about 1/6, 1/5 of the way through the competition year. So we're not super far into our designs, but we're in the initial preliminary research and some of the initial designs based on that.
So here is a budget breakdown that we've estimated for this year. See at the bottom, the total cost is estimated to be $14,500. The total that we've spent so far is $1,300. That includes $800 on a testing bed setup that we'll go over later for testing wheels, the drum design, other things that we're considering adding to the rover, as well as $500 on the testing setup for the previous rover. The software and electrical team is going to use last year's rover, which we still have, to test their autonomous system, to test out sensors, to optimize everything as best as possible before we go to the competition. The total anticipated rover cost is $4,700, which is just under double last year's cost, which was $2,600. Travel is the biggest expense by far. You can see at the bottom, it's estimated to be $9,000. So we're hoping to be able to find a way to get that money so we don't have to limit people who are able to attend the competition. And also, so far, we have received $2,000 from the NASA New York State Space Consortium grant. And what that is a panel of participants from across the state who look at projects at the collegiate level and find one that's involved in the space industry, different projects from different universities, different clubs, and disperse funds to them to allow them to pursue their projects. And next, we have some technical performance measures that we've set for this year. First is the total mass, which we have set a target value of 35 kilograms. Last year, our total mass was 28 kilograms, so there will be a slight increase, but that is because we're hoping to do a more robust and professional design. As Dylan mentioned, last year the design was more rushed. We didn't have as much money, so we did a lot of 3D printing and making ends meet for that design. So we want to have a lot better design for this year. We'll still be one of the lightest rovers at that weight. Last year, most of the rovers were in the 60 to 80 kilogram range, with the next heaviest rover being, I believe, 32 kilograms. Our next measure is the regolith payload mass. That number was based on online resources for the simulant used in the arena. We took the density of that simulant and we estimated what we think the volume of our drum might be for this year and did the simple calculation to find the total mass. The empty volume is a new measure that we introduced this year. As Dylan mentioned in the previous slide, we want to minimize the amount of volume that doesn't have anything in comparison to the overall footprint. So we're a lot more efficient in terms of volume that we take up. Our next performance measure is dust tolerance. We want to have no dust permeating through the build, as well as minimizing dust during operation. One of the main things that the competition emphasizes is dust tolerant design, because for these rovers to operate on the moon, they would get destroyed by having regolith get inside. So that's a go, no go. You get the points, you don't get the points based on that. For battery life, we want to shoot for 30 to 40 minutes of battery. The UCF competition is a 15-minute timer, and the Kennedy Space Center is 30 minutes. So we want to go a little over 30 minutes to ensure that we'll have enough battery life for that run at Kennedy Space Center should we make it. But we don't want to have too much power on board, which require a larger battery, a heavier battery. So saving mass as best as we can there. The percentage of time spent in autonomous, we're hoping to get 100% autonomy, but the statisticians in us said 99% of our time will be spent in autonomy. And the time for one cycle, we would like to be 1 minute. So that's the time from dumping to going out, collecting regolith, going back to the dumping zone, and depositing. So we want to be able to get about 12. We think we'll be able to get in the total 15-minute time before University of Central Florida.
Okay, so I'm Sujal. I'm one of the co-leads for Lunabotics. This is how our general systems diagrams looks like. We have a base station where the person controlling the rover sits. They have access to an Ethernet, which is connected to a Wi-Fi router inside the arena, and that is the only way we can connect through our rover during the whole competition period. That is through an IEEE Wi-Fi protocol. So that gives us access to all the peripherals inside the rover, including the Jetson that we are using for autonomy, and also a real-time control system, which is our STM32 microcontroller, which is using an ESP32 to interface with that Wi-Fi network. So the reason why it is 99% autonomous in the previous slides, because the person in the base station has to activate that autonomy. So that one person is basically activating that autonomy stack and then letting the rover take the rest of the 99%. The way it works is We connect to the Jetson using a remote SSH through that Wi-Fi, and then we start a script where the Jetson takes the data from the peripheral layer, which includes the depth camera, IMU, how the system health is, and also like the power sensors and LEDs to monitor how the system is working in that particular moment. And based on that, it spins ROS2, which is Report Operating System nodes that operates the navigation stack, computer vision, mission planner, and like telemetry node, which communicates with the STM32, which is our real-time microcontroller. And STM32 is capable of controlling all the peripherals, including motor drivers, ESCs, the IR sensors, and stuff. So the way this works is Jetson makes all the autonomous calls, sends the decision that it wants the rover to move in a particular way to the STM32, and then the STM32 is responsible for the movement of the rover. That's the basic systems diagram that we have created this year. And yeah, so now the question is, what if the autonomous system fails? That is how we like approached the competition last year, that we were not super confident on our autonomous systems. So we had a very robust manual control system which takes data from a handle controller into a computer which is directly connected to the Ethernet from the inside of the arena's router. Then it transports all the controllers control to that computer, and then the computer transports it to the router inside, and then the router makes an AP access point, and the rover connects to that access point, and then it receives all the manual control commands that that the person is giving to the rover. And that's how we bypass all the autonomous stack in case it fails, so our rover still runs and like completes the whole autonomy. So this year we are also including a couple of cameras on board so that we don't have to use their cameras and lose points based on that. Also, ROS2 is robust, but it can fail sometimes. Let's say suppose there is an issue with the sensor spin up, and there's an issue with like some kind of IMU issue. So we want to be able to control the rover manually, even when all of the 90% of the autonomous system fails. You can move it. Yeah.
Okay. So this is what we were mentioning beforehand is our testing setup. One thing that we wanted to do go into this year was every design choice, we wanted some reasoning behind it. So either we prototyped it, we tested it, we gathered data from it, or it's from a paper. We were really focused on like research-based designs instead of last year where we would just design something and go, this would work, and then we would do it. We didn't really have the time or the resources to test it. And this year is a very big priority. So we designed this testing setup that is both for wheels and drum, which is really nice. So essentially for the wheel design, we just have a motor attached to the wheel, and the wheel will drive itself. We'll gather data from a built-in encoder on like wheel slip, how much current was drawn, um, and try and like estimate our traction force based on that wheel design. We can design a wheel that's super rigid, but for actually maximizing the efficiency of it on like a powdery, like a sand um, substance, we can't really do too many simulations for that. And it's really hard to gather data for it. So we wanted to do it physically. And same thing for the drum. Instead of the drum driving itself, it'll be on a carriage system that we'll talk about a little bit later. We can test out different geometries for the drum, how deep it digs, how fast it rotates, just all trying to get an estimate of how can we maximize our efficiency of our wheels, the efficiency of our drum compared to the current draw output, and how can we reduce this overall forces so that we have a more efficient rover. On the right is one of our ideas for a modular wheel design that we can put on the test setup. So instead of printing out like different wheel geometries for every single design we have these like dovetail slots that we will slide and plug different, they're called grousers, but like the different rim types. So we can test different rim geometries. We can test how many rims we have or how many grouses we have. We can test how thick our wheel is if we just have like stacking plates. And all of this is just in the hopes of making our rover as efficient as possible. So we're going to go into some mechanical design. we did trade studies for pretty much every part of the rover that we could do a trade study on. These are all based on our weighted decision matrices. So we have a list of criteria for each subassembly, things that we want to look at. So like we want to reduce price, we want to reduce risk, we want to reduce the amount of forces acting on it, we want to improve efficiency. This is our first one we did. We did a belt versus chain trade study. We used a belt last year, so we only have one motor per side just to reduce weight and reduce current draw. So we had to get some power to the other wheel somehow, and so we used a belt last year. Um, it's looking like we're going to redo the belt design. It was pretty affordable. We had some more customization options with like we could 3D print our pulleys. We can get some specific ratios in there if we need to torque up our motors a little bit more. Um, Less maintenance, it reduces backlash. Chains have the advantage of being a little bit more efficient with some reduced loading capacity. But the issue with chains is that they can backdrive pretty well or pretty harshly if it doesn't like click into the sprocket super well. Um, we'll probably do some studies where we just have like belt on one side, chain on one side, and see how that goes. But we're definitely leaning more toward a belt right now. For how we want to mount our motors, last year they were mounted on the back, just directly to the back wheels, and then we had a belt go to the front wheels to connect them. Our issue with that this year is that we were already worried about being back heavy last year, but now that we're beefing up our rover even more, we're even more worried about being back heavy. So we want to try and distribute the weight a little bit more. So that kind of goes into motor mounting, where if the motors we're selecting are around like 3 kilograms each, if we can shift that more towards the middle, our weight distribution would be a lot better, and we can kind of reduce the risk of slipping or reduce the risk of getting stuck in the regolith. So we looked at, again, rear mounted, middle mounted, and front mounted motors. Rear mounted, the weight distribution, which is a really killing factor for it, while middle mounted and front mounted had the advantage of that. Overall, they weigh pretty similar amounts. Middle mounted is a little bit more expensive because we would need a right angle motor or right angle gearbox for our motors. But it definitely has the advantage of having that improved weight distribution while also keeping the middle of our rover completely open for any excavation system. So based on that trade study, we came up with a few different designs. So middle mounted would just be two separate pairs of belts per side that drives the front and back motors. We would need some sort of 90-degree gearbox to go between our two wheels. We want to keep the middle of our rover completely open so that our excavation system has no conflicts at all. So kind of just have freedom of the middle of the rover. Front mounted has better weight distribution depending on, we don't want to be too front heavy, but that probably won't be an issue. It still requires some sort of gearbox. It will just be a straight parallel gearbox, but the concern again is that the middle space is taken up, so we'd have to make some design constraints from our excavation system. But it would only be one belt and per side, so we might have some weight reduction there. For a torque analysis, it's really hard to determine how much torque our wheels need because it's not like a car on a road. You're not really looking at friction between the wheels. It's much more of a plowing motion. So like a lot of this torque analysis is a super simplified application of it where it's like flat slope. We're estimating a rolling resistance equivalent. Is technically would have to use some sort of like Terra mechanical model to get a better estimate, but just like a super rough estimate. And we can kind of figure it out through our testing setup as well, where that plan is to like add weights to the wheel setup so that we can test like how much it sinks and at what weight does the motor stop moving. So we can kind of get an estimate of how well our motor would work. It was around 14 Newton meters per torque, for 14 Newton meters per motor. And that's per motor per side. And then given the right angle motor constraints that we were talking about a little bit earlier, we selected this one from SEW Eurodrive, which we were talking with in the past. For our chassis, we did another trade study for material. This is more of like a peace of mind trade study instead of being super specific because, I mean, each one of these has 1,000 different options. Aluminum has however many compositions. So what is really important about this is selecting a few that could work and then going and doing another trade study on like specific compositions. our plan is to do FEA studies specifically on that so we can get the lowest weight and like lowest thickness of the material while still being able to handle the required forces. So we might look at a whole bunch of different aluminums with different widths, with different whatever compositions, and then do FEA studies on them, see which ones can withstand the required forces while still being low weight and low cost.
Hi, my name is Shelly. I'm part of the mechanical team for this project, focusing on the chassis and wheel design. And here we compared 5 wheel designs using weighted criteria: price, risk, force capacity, machinability, and weight. The totals are close, with fully 3D printed and metal box tie at 244, hybrid bolted grousers is 226, metal bike spokes 221, and hybrid dovetail at 195. So because the scores are tight and traction depends heavily on grouser geometry, we're not selecting a design today. The study's goal is to narrow down and prioritize prototypes. We'll build test articles and let measured performance determine the final choice. So these are the 2 active candidates that we'll prototype and evaluate. On the left is the metal box wheel with aluminum side plates and rim. It's very stiff and robust. The trade-offs are higher mass and machine time. On the right is a fully 3D printed wheel with all PETG for interlocking parts with drafted grousers. It's low cost, fast to fabricate, and easy to service. With this year's heavier rover, an all-printed structure may run near strength limits at the log roots and rims, so we're going to verify that in testing. Both designs remain open, and we'll compare with the same test procedures and let the data decide.
Hi, I'm Patrick. I'm a member of the mechanical team. We used a weighted decision matrix to determine which drum material to test for our final design. The results came out with carbon fiber at the top, and then fully 3D printed and 3D printed with metal or acrylic very close seconds and thirds. The main advantage with carbon fiber is the weight to strength ratio is very high, but the downside of that is it's very labor intensive to actually manufacture the drum, and there's a lot of uncertainty with the forces because carbon fiber is not isometric, so we have to do a lot of testing to make sure that our drum is strong where we need it to be. A fully 3D printed drum, it has the advantages of that it's easy for us to design, it's easy for us to make, and we get the material very cheap because we have free 3D printing services available for us. And then we can also use a combination of any of these technologies as well, depending if, like, for example, 3D printed ends up being better for side plates, or if carbon fiber ends up being better for the blades, just because, again, how different materials handle forces. The original design used linear actuators to lift and lower the drum, and we are trying to move away from that design, partially to shift weight elsewhere in the robot for better weight distribution, but also because a arm design can be more dust proof because you have only these 4 points where there's ball bearings instead of linear actuators, because linear actuators have a cylinder, and that allows dust to build up on all that area on the cylinder, and then it'll pull it against the seal, which leads to eventually more dust getting inside of the actuator than would get into an arm mechanism here. So for the first design, we have two arms and a single drum. One of the arms lifts the drum and lowers the drum, and the other arm simply has a belt or a chain drive in it for spinning the drum. And this is also less motors than the original design, which had a total of 3 2 linear actuators and a spinning motor. And also, the spinning motor on the first design was asymmetrical. The second design here is a single arm and with two drums on either side of it. And the advantages of that are that it could be potentially lighter, just having one arm. And there's also the potential that two drums might be more efficient than one drum. We still have more testing to do to determine that, but having both of these designs as options is really great. And both of these designs are going to be using torsion springs to offset the weight of the drum to allow us to use smaller motors that draw less power from our robot during operation.
So I'm going to talk a little bit about how we're going to test the drum in the testing setup that we're building this year. So the main things that we're going to try and determine using the testing for the drum is the operations and some of the physical parameters. Some of the physical parameters include the size of the opening. You can see the drums rotating through and scooping some of these particles here. So what size is the best for that? How deep we should be digging. Should we dig as deep as we can? Should we dig half of the entire opening? That kind of thing. And translation speed. How fast should we be driving the rover while we're digging? Is it a good idea to drive the rover at all while we're digging? As well as the rotation speed. Is the power drawn going to be worth rotating the drum faster to dig more regolith? The digging direction also is something that we didn't really consider last year, which would essentially be rotating the drum the opposite, or spinning the drum around on the axle, and so rotating it clockwise. So do we want the scoops to come over the front, or do we want the scoops to come under and from the back? We also want to test the quantity of drums. Is it better to have one drum that's wider, or do we want to have multiple drums where the angles of the scoops are offset? Which option is better for that? And we're also going to measure the effect of these parameters on the collection speed, the power consumption, how repeatable these things are for the autonomy, and the torque that's applied as well. We really just want to optimize the operation of the drum in total. And so what we have right now, you can see in the bottom left of these images, is just a basic drum design. There's nothing fancy. It's just essentially a cylinder shifted. And then you can see we've taken some dovetails out of each of the ends of the scoops. And there is a piece there to the right of it where we can model different tips to go onto the end of the drum. So we can also test if it's better to have just a flat scoop, if we want a triangular tip, if we want some other geometry that would be better for cutting through the regolith and result in less forces on the drum. Last year we did some discrete element simulations that you can see in the right there. We want to do these again this year for major alterations to the design. So a lot of those internal geometries, if we want to look into those and see what the best choice for internal is, then we can do simulations on the computer rather than having to reprint multiple different drums. So that'll keep it a lot cheaper, and it'll also be a lot faster. And for actually doing the drum tests, you can see in the top, we've designed a carriage for the drum. Like Dylan mentioned, the drum won't be able to be driven itself. We'll have a motor on the drum to rotate it, but you can see it's a little small on the slide. To the left of the carriage, we have a motor that will turn a pulley and will allow the carriage to be taken down and back across the testing chamber.
So hi, I'm Chelsea. I'm part of the mechanical team, and these are some simplified versions of my ideas to either improve the drum or kind of change it up a bit. So on the left, I call it a drum slash dumper. But the premise of it is that the orange and yellow sections are very similar to the current drum that we have. However, the inside of it is just a circle rather than having that internal geometry that the regolith has to navigate through. And then that red part is just a flat plate that would get pushed by an actuator or some other device. And when you're ready to dump, it would push it into that blue chamber, and then that blue chamber would then rotate separate from the drum to dump it out. And then the side scoop on the left is obviously it looks like a box. However, there would be some piece of rubber connected to the front of that and then through that little slit, which would be controlled to either pull it down, which would push the regolith out, or if you let the rubber go, it would fall down with the weight of the regolith. And how you would collect would just be spinning, basically, with the whole chassis to have a scoop in there. And then to let it out, you would just pull that rubber down or other material to push it out. And that's it.
So what's next for mechanical? So where we're moving from where we are right now. We're gonna hopefully begin doing the actual tests on the drum and the wheel designs. Like I mentioned, we've purchased a lot of the stuff for the final testing setup and we've started assembling it. We're gonna continue to design the raising and lowering mechanism. As Patrick was talking about, that was a big point of emphasis for this year is we wanna redesign that to make sure we're able to have a strong operation and able to dig more regolith than we were last year. We're going to do feasibility analysis of the decision matrices. The data is very useful, but we're going to have to look into how realistic some of the options are. Again, like Patrick was mentioning, it can be difficult to use carbon fiber. So maybe weighing using carbon fiber for some parts versus metal for others. We're going to begin to design based on that analysis and some of the decision matrix outcomes. And then we're going to do simulations. So it's going to be stress simulations, topology optimization potentially so we can remove some material and save weight where it's not necessary, and DEM simulations to help figure out the best way to operate the drum.
Okay, so I'll talk more into what kind of software architecture that we are focusing on. So we will have a multi-layered control system integrating Jetson or in Nano, which will handle our AI and autonomy. And we are not technically using AI, but it can be categorized as more machine learning. And on STM32, which will handle our real-time control. On Jetson or in Nano, we'll use the proven and like most of the industry standard like robotics that company uses, which is ROS2 framework for distributing node communications and mission coordination. So what it does is it takes all the data from cameras, sensors like IMU, barometer, and stuff, and then it let us communicate between different services and then make a decision that we can use to control the road. We will use free real-time operating system firmware on the STM32 because since all the data will be coming from Jetson and then also from the command center, we want some way to like use the STM32 hardware to the best of its capability. And free RTOS will give us like functions and like use cases where we can do like we can avoid race conditions and stuff so that everything is on all the time and nothing is being halted. Then it will attain some kind of a modular architecture that ensures stability and fault isolation with the fusion of ROS2 and RTOS on their respective hardware. If we go into autonomous, there are multiple steps that we need to follow. It is like perception, localization. Localization is basically where the rover is right now. So for information, the competition let us use some beacon tags, which are basically QR codes that we can put on the arena, and they have their specific locations. So we can simulate that in our test setup. and cameras which are on the rover can detect those beacons, and then using that particular beacon positioning, we can say that a rover is in this position with respect to those beacons. And then we have to plan a path and navigate. So basically, now we know where our rover is. Now we have to plan a path to go towards the digging section, and then subsequently towards the dumping section. In between, we will find some obstacles and like some different kind of terrain. We also have to do that using depth perception, using the Z2 cameras that we are using on the rover. And based on all the data that we are getting, path planning, where we are right now, that is localization, and all the obstacles that are around, we have to make decisions. And also we have to manage states. Decision in the sense which path is the best path to go to a certain point. So this is also categorized as cost maps, which are basically what is the cost of going through this route versus that route. That also happens real time using ROS2. Also, we need to implement motion control, which is basically if this is the X point that we are at, and this is the Y point that we need to be. What are the motions that we will do so that our rover is on that path and will reach there in time and then with certain accuracy. This also covers a kinematic section where we have to control a PID, proportional integral derivative controller, so that our rover is smooth and it does not have any abrupt positionings. So all of this is our autonomy stack. Everything that happens in Jetson. Now we need to find a way to communicate all of this, make a decision, and then send it to the STM32, which is actually responsible for like controlling the rover. This happens in the communication and data infrastructure section, which is also a ROS2 node. In the real-time control, we just take all the data, we send the sensor data that is actually attached to the STM32 to Jetson when needed. We handle the communication between these two peripherals and also the control system, the control tower, and then we execute the commands that are being sent to us from the Jetson. So this is basically what I just said. Core frameworks are ROS2, NAV2, which led us to navigation and localization. Um, Before testing everything on the actual rover, we'll use Gazebo to simulate everything and do stress testing based on all the possible scenarios that we will face during the run. Also, we need to be smart in choosing SLAM and visual odometry techniques, since we are using a particular type of camera and we want to minimize the power consumption. So we have to develop or identify good algorithms that will let us do that efficiently. Then we also need to find a way to plan our path in a way where we are reducing our time. We have 15 minutes and we have to maximize the amount of digging that we do. So from the starting section to the digging and dumping section, we need to reduce the time where we are traveling. So this is also one thing that we need to do a trade study on. You can go on the next slide. So this is the manual control system, which is basically being hosted on the microcontroller STM32. It will get EP interface from ESP32, which is basically connected to Wi-Fi. It will control all the data and also the movement of the rover. Now the question is, since we are only able to see or feel the rover using our joystick, how can we see the rover in actual? So we lose points to use by using their own cameras, which are inside the arena. So what I've come up with is we use a separate system where we have two cameras. One is on top of the rover, apart from the Z2s, apart from the autonomous system. This camera have a single degree of freedom. It will rotate as per the controller's choice to see where the rover is in that particular moment with respect to the arena layout. And there will be one more camera which will be facing directly towards the drum. The only issue with the navigation is that we need to know where the rover is, and the issue with the dumping and digging is that we need to know where the drum is. If we lower the drum too much, it might break. If we don't lower it enough, it might never collect anything. So we need to know exactly where the drum is, and we need to know exactly where the rover is. All of this considering that the autonomous system is not in place right now. Hopefully, we never have to use this, but this is the worst case scenario, that even if everything fails, we have something that we can utilize and then earn points. And for the matter of fact, this is the system that we used last year, and we did great to a point where we were in the middle of the section where in terms of points. So this is proven, but we want to do more. That's for autonomous. But if that fails, then we always have something to count on. You can go next. Okay, so this is tricky. Last year, due to like various reasons, we had to settle with very poor power management and electrical box. This year, we have completely changed our goal. Our goal is to minimize the failures due to electrical systems. That is to design a robust and efficient power management system. So we are customizing our power delivery, signal integrity, and signal processing to a level where it is very hard to find pre-made and on-the-shelf solutions for this. So we are attempting to make our own power distribution unit, and then also to manage all of these signals coming from STM32 to Jetson to ESP to the sensors in a single board, mainly because of the size constraint of our electrical box. And it also depends on how our mechanical team is designing our rover design. So to keep it flexible, we have chosen some components like e-fuses, robust connectors, like buck converters that are reliable and also modular, so that in future, if we ever change our design even a little bit, we don't have to redo the whole power distribution board. We can change some components, and then it will be good to go. Yeah, we can go on the next slide. Okay, so this is just an overview of like what we want to build. We want to have a good XT60 input connector from 6 volt to 48 volts, depending upon again what motor we are using. That feeds into an eFuse controlled by Jetson or STM32, depending upon the implementation, which feeds into a 5-volt buck converter and then a 3.3-volt buck converter. We might use multiple of those to supply enough current to each peripheral. Then we have Jetson STM32 motor controllers and sensors on the rail, which feeds from these different buck converters and fulfill their needs. And then we also want to use components like diodes, fuses, reverse protection MOSFETs, and then decoupling capacitors and stuff to increase our signal integrity. So last year we had this issue with our right side of the motor where there was some issue with the signals, and it was messing up with the whole electronic speed controller. So we don't want to face that problem again, so that we never have to worry about the electrical system and nothing breaks at the day of the competition. So that is the reason that why we are trying to build our separate power distribution board and investing so much into it.
All right, that concludes all of our information that we had for you guys in terms of what we've been up to. Are there any questions?